Okay, hi everybody. Yeah, today we're very happy to have Max Metlitski visiting us from MIT. Tell us about bootstrapping and defense. Yeah.
Is there a way to make it bigger?
Yes, that would be good.
Okay. Oh, there we go. And make
Okay,
it.
then maybe make that thing small.
This is better. All right. Thank you very much for the invitation and the introduction. It's great to be here. So I'd like to talk about bootstrapping line defects in conformal field theories with applications to the three-dimensional Ising model. And
You probably have to click on the slides again because you're probably in the Zoom.
okay. Menu.
Is it working on that? That one.
Yeah, so this is work done together with Ryan Lanzetta, who has recently moved to Perimeter Institute as a postdoc, and with Sheng Liu, who has recently moved to the Institute of Physics, Chinese Academy of Sciences in Beijing. And really all the credit should go to Ryan and Sheng. In particular, the main idea is Ryan's, the implementation is also Ryan. And there is some nice parallel work on the fuzzy sphere by Zheng Zhu, David de Gayota, Yin Chen He, and Yizhan Zhou that appeared last year. And throughout the talk, I'll be making comparisons between the numerical bootstrap and this exact diagonalization on the fuzzy sphere. Okay, and yeah, we hope to write this up very soon. All right, so I'll be talking about line defects in space-time, and you might ask, why should one be interested in line defects? And one reason is that whenever you have a point impurity in a quantum system, in the imaginary time or real time, doesn't matter, path integral, this maps to a line defect extended along the time direction. And the very famous example of this is the Kondo model of a magnetic impurity in a free electron gas. And the Kondo model has really been central to the developments of theoretical physics in the second half of 20th century and precipitated such developments as renormalization group by Wilson and also important progress in integrability. So we hope that by studying line defects, we can studying line defects can also precipitate such developments, perhaps in neighboring areas of physics. So in particular, I want to understand more general impurities immersed into critical systems that are more general than just a free Fermi gas. And in particular, I will be thinking about a line defect in a conformal field. Okay, and I'd like to begin with a very basic question. I would like to ask, if you have some symmetry, can the symmetry become spontaneously broken on the line defect? Right, so we know that if you have a one-dimensional classical system with a discrete symmetry, then you cannot have long-range order at any finite temperature. As long as the interactions in this one-dimensional system are local. On the other hand, if you have non-local interactions, power law interactions that fall off slowly enough, then you can actually have a long-range order in a 1D classical system at finite temperature. That's well known. So I'd like to ask, what is the analogous statement about a one-dimensional defect embedded into some bulk system described by conformal field theory? And to be very, to have something in mind, let me just consider a Ising model in d dimensions. And I'm going to tune the temperature. So I'm just thinking about a classical statistical mechanics model in d dimensions. And I'm going to tune the temperature to the bulk critical temperature, to the Curie point. And then I'm going to consider a line here. And on this line, I'm going to make the coupling between the spins much bigger than the bulk coupling, right? Such that locally the spins want to order along this line. And I want to ask, can I get long range order along the line at large enough value of the defect coupling KD? Okay, and you might think that perhaps this should be possible, right? Because perhaps because we are at the bulk critical temperature, the bulk fluctuations of the spins perhaps can induce long-range interactions between the spins on the defect, and perhaps one can kind of simulate this result from one dimensions.
And so you're tuning a parameter on the defect.
That's right. I'm just tuning the let's say nearest neighbor spin coupling along the defect while keeping the bulk coupling.
And bulk is any dimension.
Bulk is any dimension. We know the solution to this problem in 2 dimensions, and I'm going to tell you what we now understand about 3 dimensions.
And just a dumb question, the free case 4D is, what is the answer?
No, you do not get.
You don't get.
Okay,
Spontaneous.
sorry. Free case actually is quite special because free case you can get long range order in 4 dimensions. But now once you consider Ising model in 4 dimensions, because there is a marginally irrelevant perturbation, turns out there you don't get long range. Okay, there is, here I'm just thinking about a classical stat mech. You can also take a quantum perspective on this, where the 3rd dimension becomes time, right? So now I'm considering a transverse field Ising model, and I tune it to the bulk quantum critical point by tuning this H perp. And now imagine that we take one of the spins, an impurity spin, and we turn off the transverse field on this spin, right? So then sigma z on that spin is going to commute with a Hamiltonian. So I have 2 ground states, one with sigma z equal +1 and one with sigma z equal to -1. This is kind of the analog of the infinite coupling on this line defect in the StatMech model. And now the question is, okay, so of course, in the limit of 0 transverse field on this impurity spin, I have long range order in the time direction, right? Sigma z is just frozen in time. And the question is, if I imply a small value of transverse field on this impurity spin, does this freezing remain or not, right? Of course, if the spin is isolated, the moment I turn on a transverse field on it, right, then I close this spin flip processes, and the spin just points now along the x direction. But perhaps the coupling to the rest of the system, to the critical state around it, can suppress such spin flip processes. And this is actually, people have thought about this in the context of Caldera-Leggett type models of decoherence, right? There you have like a quantum spin, which is coupled to some bosonic bath, and this coupling to the bosonic bath can suppress such transitions and can lead to a freezing, if you wish, or long-range order along the time direction of the impurity spin. So in that case, it was kind of interpreted as environment collapsing the wave function of the impurity either into the up or down state. So okay, so we'll alternate between this classical and this quantum picture, but they're really the same. Okay, so what's the answer to this question? So first of all, in principle, if you have a discrete symmetry and you have a line defect embedded into a conformal field theory, can you get spontaneous breaking of that discrete symmetry on the defect? And the answer is yes. We know examples where it does happen. Now, more concrete, another question, in the three-dimensional Ising model, as I crank up this defect coupling, do I eventually get long-range order on the defect at finite value of the coupling? The answer is no. And this is a quite non-trivial result, and I'm going to give a proof of this result utilizing a numerical conformal bootstrap method.
Sorry, just a question. So you had this earlier statement that 1/r² or slower allows So naively you would expect the conformal dimensions of the bulk to be important for
That's
this
right.
question. You say, okay, if I have this thing in my spectrum, then it's allowed, and if not, if I have an operator that's
I'm going to discuss what is the criterion, what determines whether it's allowed or not. And it's not exactly the conformal dimension of the bulk, but it's certain conformal dimension of a defect changing operator on the defect.
I see. So you do need to know defect
Yeah,
physics. It's not just
so it's like I said, here it's a matter of principle, yes.
Yeah.
But in general, it's a matter of dynamics. So it's not it's
Yeah.
special to each bulk and each kind of defect type.
But your 1/r² statement might have led one to think that there's a necessary condition that you need a.
I think you're going to see how
Okay, yeah.
it comes out.
Can I ask also, this defect in the Ising model, are we getting only one conformal defect as we raise K, or are different Ks different conformal defects?
You can ask, okay, so your question is, at large finite KD, if it doesn't flow to this long-range ordered fixed point, what does it flow to? And just flows back to transparent defect. I think that's we can't prove that, but that's the expectation, that it just flows to the transparent defect. I'll have a slide on that. So KD equal to K. So there is a kind of analogous question that you can ask about continuous symmetries, and in particular, spontaneous breaking of continuous symmetry on two-dimensional defects, either interfaces or boundaries in a CFT. And of course, for two-dimensional standalone system, we know that you cannot get true long-range order at finite temperature. That's the Mermin-Wagner-Hohenberg-Coleman theorem. Well, what about on a, let's say, 2D interface or 2D boundary in a CFT? And here, turns out that the generic statement is, again, that you cannot get true long-range order, but you can get very close. You can get these correlation functions of the order parameter decaying as a power of logarithm of the separation. So it turns out this behavior is actually realized in the ON model at a boundary or interface. So this turns out to be generically the closest that you can get to.
Is that formula also supposed to be true when X is small?
No, this is for large.
It's only for large X.
Separation. Yeah, this is the asymptotic. Yeah. So it's almost ordered, but not quite. So okay. In contrast, for 1D line defects and discrete symmetry, you can break in principle, but for Ising it doesn't happen. Okay, so let's first remind ourselves, why don't we get a long-range order in one dimension at finite temperature? And of course, the reason is domain walls, right? If we start with an ordered state and we consider a domain wall, here I'm just going to be thinking in the context of the Ising model. The domain wall costs an energy which is constant in system size, but you can place the domain wall anywhere, so the entropy of the domain wall grows logarithmically with the system size. So at any finite temperature, domain walls proliferate, entropy wins. Now, in contrast, let's think about a line defect embedded into a conformal field theory, and let's fix the spins on this line defect, kind of like a fixed spin boundary condition. And let me ask, what is the free energy cost of creating two domain walls separated by distance L? And generically, this will also now scale as a logarithm of the separation of the domain walls. Why do I say free energy? Well, it's because all the spins in the bulk are now going to fluctuate in the presence of these boundary conditions. So now you have a non-trivial competition between the free energy of the domain wall and the entropy of domain wall positions. So which one wins is a matter of details. Okay, so how do we think about this systematically? Well, first let's think about a situation where we just freeze all the spins along the defect, let's say to plus, all right? Well, we expect that that should be the same as starting, here I'm working on the lattice, but we expect that to be the same as working in the continuum with the Ising CFT and turning on the relevant perturbation sigma on this line, sigma being the order parameter of the Ising model. This is relevant because the dimension of sigma is close to 1/2. So we expect this to flow to some conformal line defect in the infrared, which will have a remainder of the bulk conformal symmetry, namely it will have translations along the line, it will have the scale invariance, and it will have invariance under special conformal transformations along this third direction. And of course, we'll have the rotational symmetry around the line defect and all the whatever reflection symmetries that the defect preserves. Okay, so this is if I'll call this defect D plus, this fixed spin, or sometimes people call it pinning field defect. You can also break, of course, the Ising symmetry in the opposite way, and that defect I'll call T minus. So we expect these defects to exist in the 3D Ising model. And of course, these defects come with their own local operators, spectrum of local operators localized on the defect. And we can organize them into towers under the remaining conformal symmetry SL2R, and they're going to be characterized by the scaling dimension and the spin associated with this transverse rotation around the line. In addition to these local defect operators, I can also consider so-called defect changing operators, right? Where I take a junction of two types of defects. Let's say in this case, it's the pinned plus and pinned minus, right? And I can, there is a junction, and there are operators that live at that junction, and they again are going to be organized into conformal towers, characterized by scaling dimension and spin. So you might be familiar with such defect changing operators from two-dimensional conformal field theory. Carty considered them, there he considered them in terms of boundary condition changing operators. Well, this is a simple generalization to line defects in a higher dimension. Okay, so this is the story with the pinning field defect, where I kind of impose the states of the spin. Now, let's come back to the problem we want to understand, which is if we preserve the Ising symmetry, right? So we have an Ising model, we have a coupling along this defect line. And let's begin with a case when this coupling is infinite, right? If the coupling is infinite, then all the spins along the line are either all plus or all minus, right? So then this line is just a direct sum of this pinned plus and pinned minus lines. What are the local operators of such a direct sum fixed point? Well, we have the local operators of the plus line and the minus line, but we also have now the defect changing operators, which I'll refer to as domain walls. So these now also become local operators of this fixed point. And we expect that the minute you make this defect coupling large but finite, then it will induce these domain wall operators. So in order for this fixed point KD equal infinity to be stable, the scaling dimension of the lowest domain wall operator has to be greater than 1. That's the stability condition. And of course, I should make it obvious that this KD equal infinity fixed point, it has long range order along the defect. If delta plus minus is smaller than 1, then the domain wall is relevant, and we expect the long range order to be unstable. And we will prove that actually the lowest dimension domain wall in the 3D Ising model actually has scaling dimension less than 1, so long range order is unstable.
So this one is kind of the 1/r², yes, right? The 2 is 1 plus 1. Is that the same?
Well, in
Or,
if you
I guess that, it makes sense that this is the criteria for stability, but then from the other picture, you would have said, I need some, I would have thought that it was an operator in the bulk that has dimension less, that needs to be relevant enough to induce a 1/r².
I think you may be thinking about the free theory in the bulk, right? So if you take let's say 4-dimensional theory and a line defect, then you will exactly induce, if you think about the interactions on the defect, there will be 1/r² interactions.
As the border, no, I'm saying in general, that's the borderline case, right? R²
What?
is the borderline case to allow for spontaneous symmetry breaking.
But I think here you shouldn't think about it that way. You really should think about it you should really think about generically in a CFT.
Yeah.
The energy cost of this domain wall pair
Yeah.
will grow logarithmically with L because these domain wall operators will carry a fixed scaling dimension, which means that if I consider a correlator of 2 domain walls like this, relative to no domain wall, it will go as 1/L to 2 delta plus minus. Then you take the log, the free energy goes logarithmically. So somehow.
But I think it's the same condition because the dimension 1 operator would have 1/r² 2-point function, and that's kind of the force mediated. I think it is kind of the same criteria.
You're right that if you have a non-local interaction that goes as 1/r². Okay, I won't scroll back.
It's 1/r² or longer range, right? So it's the same criteria as delta equals 1 or smaller.
No. I think 1/r² gives you domain wall interactions that go as log L.
Yes.
And the coefficient can be arbitrary. So you can tune the coefficient such that it becomes irrelevant. If you have interactions which decay slower than 1/r², then actually the interaction energy between the free energy here doesn't grow logarithmically, but grows faster. So it has some power of L, right? So then you always then the order state kind of becomes super stable. It's not even a marginal case, right? So delta plus minus is kind of the coefficient of this log, and then the 1/r² is just the fact that you have a log and not a power of L.
Okay.
So the picture I should think is that the bulk interactions somehow generate those domain walls on those the domain wall changing or defect operators is O plus minus.
I think you can begin by starting with this KD equal infinity fixed point, right? And here just all the spins are fixed to be, let's say, plus or minus, right? And now the moment you make KD finite, then you can have configurations at a finite energy cost where you flip some of the spins.
Is KD equals infinity, does that actually define a conformal line defect in the Ising model?
No, a non-simple one, which is a direct term of this.
I see.
Maybe it's also will become more transparent if you think about the quantum language, right? So here again, remember we have this situation when if you turn off the transverse field on the impurity, then the impurity spin can be either plus or minus 1. If it's plus 1, right, that sector, that's like the plus sector. If it's minus 1, it's the minus sector. Have a direct sum of those Hilbert spaces.
Great.
And now you turn back on sigma x, small sigma x on that impurity, right? It's going to flip you from plus to minus or minus to plus, right? So that directly introduces this domain wall operator. So it perturbs your fixed point, this non-simple line, by domain wall operators. I'll prove that these domain wall operators are relevant. And then the question someone already asked, where is the flow towards? And the guess is that the flow towards the transparent line where H perp on the impurity is equal to H perp in the bulk. And at least we know that that transparent line defect is stable to Z2 preserving perturbations because the epsilon operator in the Z2 even operator in the Ising model has dimension something like 1.4, right? So this perturbation is irrelevant.
Is this question at all directly related to the pinning surface defect?
Well, the surface is a different.
I know it's different, but we know some things about that defect also, so I'm wondering.
You want to dimensionally.
I'm wondering if our knowledge of, if there's some relation between what we know.
Not direct, but maybe there is something one can. Yeah.
When you say defect, do you mean different value of coupling constant only, right?
On the line, exactly. That's it. So, okay, so before my main goal is to talk about the case of three-dimensional bulk, three-dimensional classical or 2+1 quantum, but let me first remind you what is known about 1+1 or 2D classical. Okay, so first of all, there is a pinning field defect, right, where we fix the boundary condition on an interface or line here. And it turns out in the IR, this cuts your system into two halves, right, where each boundary here has a fixed boundary condition. Now you can ask, okay, what is the domain wall, right? So you have to flip both boundaries from minus to plus. That's a product of domain walls on each kind of exposed boundary. The scaling dimension of this boundary, now this is really boundary condition changing operator, this phi plus minus 1, is equal to 1/2 in the Ising model. So product of them on both boundaries has scaling dimension 1, so it's marginal. And it turns out to be exactly marginal. And in fact, it generates, if you tune the coefficient of this domain wall operator, it generates a line of fixed points, where on one end you have this fixed boundary condition. On the other end, you have a product of free boundary conditions on both the left and the right. And in the middle, there is a transparent line defect. So this is the story about 2D. So in 2D, you only get long range order along this line defect, only at the very end of this defect conformal manifold. Anywhere else on the conformal manifold, you have correlation functions along the defect that fall off in a power law manner.
But it's always factorized, yeah? For all values of the coupling, it's factorized.
It's not factorized. You can think
Oh, I
about,
see, because only on the extreme left, you say it's factorized.
it's factorized on the extreme left and on the extreme right. Here it's actually transparent, right? So it's kind of fully glued.
Yeah.
And more generally, you can play the folding trick and you can think about these as boundary conditions in some orbifold C=1.
There are claims that in 3D Ising, the pinning defect is also factorized. You have opinions about those?
Pinning defect, two-dimensional
Yeah,
pinning
yeah.
is also factorized?
Yeah.
No, I think that's that's common law, and I think there is nothing contradicting that common law. It's known from numerical simulations, and it's known from like you can think about large N expansion. Basically, the dimension of the sigma on one of the boundaries is greater than 1, and then the coupling is irrelevant. It's also known from Monte Carlo and fuzzy sphere. So for many.
But this does not affect our knowledge of the pinning line defect in any way. This was the kind of thing that I was wondering about.
I don't see it directly. Okay, so let's get back to the 3D case, right? So we have this pinning. We're really interested in the spinning field defect, and we are interested in kind of defects on the pinning field defect, that is the defect changing operators and their spectrum. So the question is how we want to solve this problem using bootstrap. How do we bootstrap such line defects? And actually bootstrapping, okay, so first let me give you a quick reminder about how bootstrap works in the bulk. Bootstrap. So we are starting a conformal field theory in the bulk. And so bootstrap is a powerful method that relies just on unitarity and conformal invariance and other symmetries. So the main players are local operators that organize themselves into towers under the conformal symmetry with primaries carrying a well-defined scaling dimension. And then there is the operator product expansion, right, of two primaries, where you write this product as a sum of other primaries and their descendants. And the most important thing is that the coefficients of the descendants in this expansion are fixed in terms of the coefficient of the primary, lambda ijk. So this is the 3-point functions. And then if you say, okay, have a 4-point function, then you can expand this 4-point function in two ways. You can either think about fusing x1 and x2, x3, and x4, and using this OPE, or you can do it the other way around, x1 and x4, and x2 and x3. And the two sides have to be the same. This is known as the crossing equation. And the very nice thing is that well, first of all, if you rewrite this crossing equation, let's say just in the case when all the operators are the same, just same kind of operators at all these 4 points, then what appears here on each side is the square of the OP coefficients. And in the unitary theory, this square is a positive number. And then you can, so it's basically have a sum of positive numbers times some vector is equal to 0. And then you can use linear programming techniques to kind of rule out solutions to that equations in certain regions of parameter space, that is for certain types of spectra of operators. So that's the idea of conformal bootstrap, and it's been extremely successful in studying conformal field theories such as the 3D Ising model, right? So here, the famous island that you get, right, that you can now constrain the scaling dimensions of the two lowest dimension operators in the 3D Ising model to many decimal places. This is not even the most recent result. Recently, people have been able to push this to a couple more decimal points. So it's extremely successful program in that case. And the question is, how to generalize it to defects, to study defects in conformal field theories.
Sorry,
yes.
but before trying bootstrap, you may try perturbation theory.
And people have, so there is, for this pinning field defect, there is very nice epsilon expansion that you can start with 4 dimensions. There, the turning on sigma on the line is marginal. You go to 4 minus epsilon, becomes slightly relevant. There is a fixed point. People have worked out first few orders. So it's not, and you can also do large n directly in 3 dimensions, start with the ON model.
But perturbation expansion in first, second loop indicates the transition.
There is a fixed point. There is a defect fixed point, as there should be, right? Because this has to flow somewhere. And we can access that fixed point in epsilon expansion. And we can also compute these scaling dimensions of defect operators that I call delta plus minus here. And in 4 dimensions, this delta plus minus is equal to point, or in 4 minus epsilon, as epsilon goes to 0, this is equal to 0.45. So it's marginal, so it's relevant. And then in 2 dimensions, it's 1. So the naive expectation is that as d goes from 4 to 2, this scaling dimension grows from 0.45 to 1, but remains relevant. So there is no long range order anywhere between 2 and 4 dimensions. But we are going to now see that with bootstrap. Okay, but the problem with bootstrap, kind of for any dimension defect, is okay. So what can you study? For instance, you can study correlation functions of bulk operators in the presence of defect. And already 2-point function turns out to be non-trivial. And this 2-point function you can expand in 2 ways. Again, you can either think about taking the bulk operator and writing it as a sum of defect operators, and then taking expectation value of two defect operators. And in this channel, you do have positivity. You have a sum of OP coefficients squared, bulk to boundary OP coefficients squared. The other channel in which you can expand is you can think about bulk operator product expansion, fuse x1 and x2 first, and that gives you an expectation value of the resulting operator in the presence of the defect. There is no positivity in this channel, right? You get a product of expectation value of the operator times the OP coefficient. No reason for that to be positive. So this is the problem, that usual linear programming or semi-definite programming techniques do not, even though you have a nice crossing equation, but you don't have positivity in that crossing equation. You can say, okay, why don't I instead just study correlation functions along the defect, right? For instance, here's a 4-point function on the defect. It has the same, I can now just think about defect as its own separate world, and I can just apply, if the defect has dimension p, I just apply p-dimensional conformal bootstrap to this defect. Perfect. There is positivity in the 4-point function crossing equation. All good. Problem is, how do you put in the information that this is a defect sitting in some bulk, right? That information about the bulk is completely lost here. Okay, so that's the challenge. So for line defects, or certain types of line defects, we've been able to circumvent this challenge. And the idea that really goes back to a paper by Ryan Lanzetta and Lukasz Witkowski, so Ryan is my collaborator, is that you should think about defect endpoints. Right, so here's your line defect of some type, and think about just terminating it at a point. You can think of this as a defect changing operator from a transparent line, trivial line, and this non-trivial line. And okay, so this will also organize themselves into conformal towers under the remaining SL to R symmetry along the defect. And Ryan initially in this paper studied such endpoint operators when A was he was working in 2 dimensions, and this was a monodromy defect such that the A line was topological. But now we want to, what we realized now is that you can also extend this to the case when the A line is non-topological. So the idea is to think about the following configuration where you have 2 segments, hubs of different types, 2 line segments of different types, and you just want to calculate the partition function in the presence of these 2 line segments. So let's demonstrate how that works with the 3D Ising model. So suppose you have a pinning field defect here and a pinning field defect here of the same sign. And they're in this collinear configuration, right? So if you look from very far, this segment is very small, so it looks like a local operator. And same with this segment, looks like a local operator. So then this just fuse into local bulk operators. So this way you get access to the bulk spectrum. If you fuse like this, you bring x2 and x3 close together, it becomes a defect operator, right? So this crossing equation will link spectrum of bulk operators to the spectrum of defect operators on this red, which is pinning plus defect.
Okay, so on the left hand side, you have 2 bulk operators in the end, and then on the right hand side you have 3 defect operators on the red line.
So it becomes a 3-point function, right?
Why is there positivity on that 3-point function? If you keep going to evaluate, won't you get cubes of OP coefficients?
Well, but when you fuse, it's same as 4-point function in 1D. Think about it that way. So you get an OP coefficient here, but you also get OP coefficient in the 3-point function. It's the same. If these endpoints are all the same operator, which will take them
to not bring x1 to x4 without having it pass through the intermediate point if you keep them in that configuration, right? You can only do OPE if they're nearest to each other.
Yeah, but in the end,
but you can think about it as a circle if you prefer to think about it that way. But you don't even need to, right? You can think one D line is conformally equivalent to a circle.
Yeah, I mean, or more simply like you bring 2 and 3 together, that creates one thing, and then the end thing is the 3 point, which is another OP coefficient. So
That's
you have OP coefficient squared.
Yes.
Can you bring x1 and x4 to infinity?
Can you map x1 and
Yeah, just extend them to infinity and just think of a point at infinity.
yeah, you can say it's same as one-dimensional conformal field theory. Okay, here's another correlator we can consider. Instead of same sign of symmetry breaking, think about different signs of symmetry breaking on the two defects. Right, so if you fuse in this channel, we again get local operators. If you fuse now in this channel, well, we get a domain wall between plus and minus. So we can also access domain wall operators with this scheme. And finally, we can, instead of considering two line segments, consider one line segment and two local bulk operators, right? So again, here you fuse into the bulk channel. Here we take one of the local operators, bring it near the defect. Well, that becomes some new defect operator. You can write that in terms of all the defect endpoint operators in your theory. So the spectrum of this will also enter. Okay, so this is going to be at the end the system of correlators we consider. Going to be two segments, defect segments of the same type, two defect segments of opposite symmetry breaking, single segment mixed with two sigmas, sigma epsilon and epsilon epsilon. Remember, these are the Z2 odd and Z2 even fields of the bulk Ising, and just 4-point functions of Ising in a collinear geometry. We're always going to work in a collinear geometry like this, such that we have a remaining one-dimensional conformal symmetry SL2R, and we're just going to think of this as a one-dimensional bootstrap problem. Or I should say that these endpoints, defect endpoints, like I said, there is a spectrum of them, and we always take the external operators here to be the lowest dimension endpoint. Okay. And surprisingly, actually, our method can access a quantity which is the defect central charge. So you might be familiar with this from two-dimensional conformal field theory, boundary conformal field theory, where it denotes the boundary zero temperature entropy. Well, there's a generalization of this quantity to any dimension, to line defects of in any bulk dimension, where you just consider a partition function of a circle in the bulk circle defect, and the universal part of this expectation value is the defect G function, which has actually been proven to be a renormalization group monotone. So monotonic under defect renormalization group flows. And we can access this quantity with our bootstrap in the following way. So let's normalize our endpoint operators in a standard way to 1. Then let's consider fusion of endpoints in this channel here. Okay, so you're going to get, if you bring them together close, you're going to get defect operators, and one of the defect operators is just identity. With what coefficient does this identity appear? Turns out it appears exactly with coefficient 1 over G. And one way to think about it is think about this not a full circle, but kind of circle minus a small segment, right? And bring these two endpoints together. You use this operator product expansion with 1 over G. So you're going to get 1 over G times the full circle, which is G. So that works out. Okay, so again, we're going to study this system of correlators, and we are going to, because it's an inside bulk 3D Ising model, we know a lot about the 3D Ising model, right? We know the spectrum quite well. So first of all, we know, like I said, the spectrum, the dimensions of sigma and epsilon to very high accuracy, and I'm just going to hardwire them in, and I'm also going to hardwire the OPE coefficients in. And in addition, for the excited spectrum, from combination of bootstrap and fuzzy sphere, we believe that we know the locations of all the operators of dimensions smaller or equal than 6 to varying degree of precision, but basically we are going to put that information in, and when we don't know the when we are not very sure about the precision, we are going to be very, very generous with the error bar.
Sorry, the only ingredients that you had previously was from the bulk was just sigma and epsilon, right? In which place do you need all these other?
So because we have this fusion because we have fusion in the bulk operators, for instance, here and here and here, or also here, in the kind of low dimensional part of the spectrum in the crossing equation, they're just going to impose that the only operators live in these intervals here. Live are just these ones. The only bulk operators are these ones, and we allow for a kind of window for them to live in.
That's your bootstrap input.
We put that in.
But do you need to? I thought that you just need to solve this, systems of crossing equations with the positivity.
You can, but we would like to somehow utilize as much knowledge of the bulk as we can.
I see. So A part you didn't need to, but this is something that
We want
is
to get as strong constraints as we can.
Do you impose them as like gap assumptions?
This you can think of this as gap assumption.
Usually you need gap assumption to get like a finite window for your boundary.
Yeah, absolutely. So here, I don't know how sensitive we are to the high dimension ones here in particular, but we just kind of you can start dropping later on. Okay. All right. So like I said, some of these operators fuse into bulk operators, and but we organize, we organize our bootstrap because we're only working on a line. So all operators are written in terms of SL2R conformal towers. Now, some bulk descendants are actually SL2R primaries. So some of these SL2R primaries here, we know, like here, I write an example of a bulk descendant, bulk operator descendant, which is descendant at level 2, which is an SL2R primary for this conformal transformation along the line. And the OP coefficients of such bulk descendants are known in terms of the OP coefficient with the primary. So we put that information in. Now, of course, if I have a 3-point function where I have a bulk descendant here, but here I only have this defect endpoint operators. This 3-point function is not known in terms of the 3-point function just with the bulk primary phi. So that's kind of the reason why we cannot put in the full 3D conformal symmetry for all operators, for all bulk operators appearing in this fusion. But for the low dimension part, we can, and for instance, we put it in explicitly for this operator sigma to epsilon 2 and epsilon prime 2. Okay, so that's the setup, and now what do we get? Well, we have bootstrapper's dream is you get an island. So how to read this plot, right? So horizontal axis is the scaling dimension of the defect and endpoint operator. Vertical axis is the ratio of these 3-point correlators, defect and sigma and defect and epsilon. The only assumptions that go into this left plot here is that the pinning field defect is stable, right? That all the local operators on the pinning field defect have dimension larger than 1. And you immediately isolate this island. And we believe that this physical pinning field defect based on epsilon expansion, Monte Carlo, fuzzy sphere lives in this island. The different colors correspond to increasing the number of derivatives. So you see that there is a continent, but the continent seems to be receding as you increase the number of derivatives. But okay, you have this nice island. Now, if you allow yourself to make more aggressive gap assumptions about the defect spectrum based, say, on epsilon expansion of fuzzy sphere results, then you can start shrinking this island, and you can shrink it even with a fairly conservative gap assumptions based on what we know from, let's say, fuzzy sphere. We can shrink this island a lot to this little nugget shown here, and then the pink region is the fuzzy sphere. Is the fuzzy sphere result, the pink box. So you see, we quite competitive with the fuzzy sphere, but actually the best way is you can kind of use some of the input from the fuzzy sphere to increase the precision of the conformal bootstrap. Here is the perhaps the most important physically plot. So here is the scaling dimension of the domain wall operator, lowest domain wall operator. Again, under the minimal assumption that the pinning field defect is stable. And you're scanning over the size of this island here. And you see that everywhere this domain wall dimension is smaller than 1. So we conclude that necessarily the domain wall is relevant and long range order along the defect is unstable. Now, here's a small caveat. What we proved, strictly speaking, is that this line defect d plus plus d minus that we expect that we'll get in the limit of infinite coupling along the defect is unstable. Now you could imagine that you perturb your Ising model, either the classical one or the quantum one, in some highly non-trivial way on this line defect, such that you realize some other kind of direct sum of pinning field defects sitting here, right? Then in principle it could still be stable. So we do not rule out long-range order on any line defect in the Ising model. But I think for this one, where we just have a simple coupling KD that grows, we do rule it out. Okay, so there are some other general bounds on other operators that we get. Here is, for instance, the local operator on the defect. And you see it has some nice kink here. Pink box again is fuzzy sphere. And this is the lowest, the next lowest defect endpoint. And there is again a kink, and the pink is a fuzzy sphere. So this is again with minimal assumptions. And it seems like the physical theory lives close to this kink. Here's the G function. Remember, I told you that we can extract the G function. And so with the most general assumptions, you get this big blue egg, talking about Easter. Now, this egg, you see G is everywhere smaller than 1 and everywhere greater than 1/2. And that's quite important because we know that this pinning field defect we can get by starting with a transparent defect and turning on the relevant perturbation sigma along the defect. And transparent defect has G equal 1, so G plus better be smaller than 1 if monotonicity is obeyed. The other fact is, here we conclude that the direct sum defect, d plus plus d minus, is unstable to domain walls. The guess is that it flows to the transparent defect under the domain wall perturbation. And for this to happen, G plus needs to be greater than 1/2. Okay, it's greater than 1/2, so everything is consistent. So this is just with minimal assumptions, this big blue egg. And then if you kind of crank up the assumptions the same way that we did here, but still kind of quite conservative, you can shrink this blue egg to this little nugget, dark blue nugget, and pink is the fuzzy sphere box. So okay, we again can beat fuzzy sphere. Notice there is a nice kink on this nugget here, and if you look at so whenever you are near a boundary of an allowed region, you get a solution to crossing, so-called extremal solution to crossing. So you can look at the spectrum of operators corresponding to that extremal solution, and when you're close to the kink here, you actually, few low dimension operators agree very nicely with what we know from fuzzy sphere exact diagonalization. So I'll just show you some comparisons. So this is the with these non-minimal but still quite conservative gap assumptions. These are the rigorous bootstrap bounds that we get. These are the values that we obtain from this G minimization, where we look at the lower boundary of the G close to this nugget. And these are the values from the fuzzy sphere. And you see that we agree quite nicely with the fuzzy sphere. Okay, so I guess I'm running out of time. Let me talk about the outlook. So we developed a novel method to describe, to bootstrap line defects. Works for line defects that can end. It's already quite successful applied to the three-dimensional Ising model. One direction where I think improvement is possible is to put in more of the bulk three-dimensional conformal symmetry. So here, in our system of crossing equation, we consider these pure correlators of pure bulk operators, and we expand them in terms of one-dimensional conformal blocks. Now, they can also be expanded in terms of the three-dimensional conformal blocks. So we can keep that as a separate crossing equation, and then we can kind of link the low-dimensional part of the spectrum, and I think this will improve our accuracy. And the next direction is extend to other conformal field theories, and particularly we hope to be able to study Wilson line segments in QED3, and bootstrapping the bulk spectrum of QED3 is a long-standing problem, and the hope is that perhaps if you incorporate line segments into your bootstrap, maybe you can get some mileage out of that. Maybe you can put in quantum numbers of these endpoints under the global symmetry and so forth. So have some hope there. Okay.
Sorry, but your defect doesn't have ends. You have a closed loop or
No, we have segments like this.
segments?
Yeah, finite segment.
But its size supposed to be comparable with the bulk size of the bulk.
So the only thing that matters, right, is kind of the so-called cross ratios. Think about this as a 4-point function, right? And the conformal cross ratio is the important, because it's conformal, right? So the only thing that matters is this relative length. We already kind of interpret.
Let me ask a question. I don't want to think of this way. Suppose I have a system on a torus.
Yes.
And the defect is it's one-dimensional defect, right?
Yes.
The one-dimensional defect is a cycle of this torus.
Yes.
No ends.
Yes.
Equal size. Not just
Yeah. That we do not know how to study.
So you have defect with ends, and its size is smaller than the system size.
Smaller than the system size.
So you're saying that it's a really correlation function, right?
It's really correlation.
So you don't study defect, you study correlation function. Is this right? Could I say this?
But it's not a correlation function of local operator.
Whatever. Yeah, for example, take an Ising model, you can study disorder operator, right? Or you can study
But those
spin or
those are topological line defects. These are not topological, right? In the sense that if I change the path of this red segment to something like this, I'll get a different. I got a different value.
Right. But the story is reduced to a correlation function.
They reduce the correlation,
We should,
but just not.
operator may not be local, but it's a correlation function of certain operators.
Agreed.
And then it's a question of how this correlation function change
Yes.
with the distance. Thank you.
Yes.
So 5 plus 0 is the operator that gives you the start of the defect. It's like in contrast to the domain wall, right?
Yeah.
So in QED3, the hope is to assume conformal symmetry and see, maybe roll it out or see if that is possible.
That's right. That's right. Yeah.
And you mentioned Kondo. Can you illustrate it on that example?
Ah. So in the Kondo case, it's a two-dimensional CFT, right, with some boundary. So then you're bootstrapping boundary conditions in the Kondo in a two-dimensional CFT. People have done some work on that in the past, actually, but I don't think I don't know.
But can your results be illustrated in that language?
What exactly do you mean by illustrated? So I think we can do like two-dimensional. Remember, I mentioned this problem here.
Illustrated means specified. Two.
We've tried it explicitly for what is it? For 2D easing with an interface to study the spinning field defect in 2D easing, and we also get an island. So for Kondo we haven't tried, but people have in general for these boundary condition changing operators. I think people have done at least some work in 2D, but not using this 4-point function bootstrap, not using correlators, but using this partition function bootstrap, where you think about your partition function of a interval, and then you write it in two ways, either in terms of closed string or open string. Yeah, I don't think this 4-point function boundary bootstrap has been done for the 2D CFT. Yes.
So maybe in QED3, but not as Ising. I guess if there's some extra like global symmetry that talks to these line defects, these would play some role in constraining something.
Absolutely. Like you could, for instance, often these endpoints here transform in some way under the global symmetry in some projective way, right? So then you would be able to put that in. So maybe like part of the problem with QED3, right, is like you're bootstrapping maybe operators like psi bar psi or something like that, that already kind of composites of, if you wish, the quark fields. So maybe this is like you get more hands-on to the quarks. So maybe one can somehow marry the one-dimensional constraints from the lines, and then for these bulk correlators, we can use 3D blocks, kind of utilize more of the 3D conformal symmetry. Maybe with that, you'll have some success.
Well, if there are no more questions, let's thank Max for
So Max, if we have a tiny surface, but we make it cylindrically shaped,
Aha.
extended in time. Well, I'm wondering if that's somehow related in the limit of small radius to the pinning.
It would be.